So I will talk about this approach that we developed to use machine learning for inverting the spectra rather, to obtain structural characteristics of materials using their X-ray absorption nearest structure or X-ray absorption fine structure data. And this is the approach that I presented in a few times, and I know that some people here already heard my talks, but I will update you on the latest developments. And for those who don't know this approach, then I'll try to make it also sufficiently comprehensive that you will understand from the beginning what is it about. So as the picture on the left shows, the idea is to take the spectrum and map it on the structural characteristics such as coordination numbers of a nanoparticle, or it could be interatomic distances, or pretty much those descriptors of structure or electronic properties that inform the spectra. And the mapping is done by using this artificial neural network in which this relationship is embedded in the operations of the neural network that sends signals from one node to the other using well-defined mathematical functions. So the neural network is a function that takes input and makes an output. And we apply this function to solve the inverse problem, how to obtain structure from the spectrum. So in the past, we started with nanoparticles, and lately we have shown this approach applicable to a larger number of materials, from size-selective clusters in the bottom to some non-metallic species to bimetallic nanoparticles. We use this approach to apply it to not XANES but to X-ray absorption fine structure, to XAFS, and demonstrated that it can be mapped not on the coordination numbers but on a more important characteristic, the radial distribution function in those cases. And that opens a new opportunity to study not just some end states of the transformation, but the process of transformation itself, in which traditional XAFS methods usually break down. So these are some snapshots of what we have learned from this method, and I will walk you through some basic ideas. So why to study nanoparticle structure? Well, the particles are small enough that in many applications they can be useful in size range from just a few atoms to few tens to 100 atoms, that there is a temptation to learn where the atoms are located and what's the relationship between their location and the properties. But of course, it's impossible to reliably obtain the XYZ coordinates of all these atoms, and people have to settle for something more sort of indirect or effective information rather than this detailed information. And this is what we call descriptors. What are the structural descriptors that matter for explaining materials properties? And for a long time, the nanoparticles could be understood in terms of just one parameter, the size. And the size affected quite a few things, and it was considered to be the most important knob, the most important tuning parameter that affects their properties. And from 18th century, we know about Laplace's law, that the latest parameter changes with the particle size, thermal properties, melting point changes, the HOMO-LUMO gap, Kubo gap in electronic states changes, and the yield strength in mechanical properties. And this is just a few examples. So size is a good property descriptor, and if it was just the size, we could probably make do with simple approach, but we want to learn more than the size. And we learned from our work and from work of others that in catalysis, for example, the descriptors affecting the properties and the function go beyond the size. For example, the shape, like in the middle figure here, and I probably will use a cursor or a pointer, these shapes turn out to be important for explaining the reactivity of this platinum catalyst, namely the onset temperature of its active state for converting for oxidizing isopropanol, make acetone. And so different shapes had different number of 1-1-1 facets, and that was attributed to be the main reason why the different particles are more active at different temperatures. Then the role of strain was highlighted in recent work, where in this case there were platinum particles, platinum copper core shell particles with platinum in the shell, and different thickness of the shell was responsible for different activity, and it was attributed to different strains. So all these attributes are related to XYZ coordinates, but they are more useful because for once you can get the hundreds of coordinates out of the data, but you may be able to get 2 or 3 numbers out of the data, such as coordination numbers, interatomic distance, and such. And so that's what we're after. We wanted to get coordination numbers out of our spectra to model the size and shape of these particles. And this is just one example of important material, but those ideas, of course, are as universal as the whole reason why XAFS is so useful technique, because it can be used to analyze very large class of materials. And for all of them, we need to know this type of information. Coordination numbers, bond strain, electronic descriptors such as d-band center. So all this is important. And for many years, we relied on XAFS as the sole source of this information. I'm talking about structural, such as coordination numbers and interatomic distances, for example. Because we take an equation, we feed it to the data, we get the adjustable parameters out of the best fit, and we report them as the best fit results. And what we do with them, we answer the main questions we set out to answer is, for example, what's the shape and the size of the nanoparticle? And you can use it by simple models, where you start with some kind of polyhedral structure and see how that structural properties such as coordination numbers change as a function of the diameter, and you have nice dependence, and so you can map it to experimental data and get the answers about the actual object without going into XYZ coordinates of each atom. So the goal is achieved if you can get these coordination numbers, and you can do some more advanced studies like shown here. But this is the point. So we find, and I'm skipping a lot of steps here because it's a short talk, we find that this XAFS analysis that has been a workhorse for many years becomes problematic. If you have a system functional catalyst with a low weight loading to make it more realistic, at harsh reaction conditions, studied in operando, that means with thick reactor walls sometimes, with a data quality that may not be giving you sufficient extent of XAFS range to get this coordination numbers reliably, because in the end of the day, you get them from the fit. And to get a good fit, you need to have sufficiently good information content in the data, and that's where you get stuck with this operando processes. So what can be done instead? We can look at the XANES, which does have many type of many pieces of information that we need, but it's all encoded in a very non-transparent way in the data, much less transparent than XAFS, because in XAFS we get an equation, and here we don't. So we tried to learn what does, well, not we, many people who model XANES, of course, know how sensitive XANES is to the three-dimensional geometry of the nearest environment of the absorber. And here's just one or two examples. If you take just a dimer and run FEF calculation and change the distance between the atoms in this copper dimer, you have this huge response. And that shows that there is a strong sensitivity in the XANES, what people know, but we wanted to see how it can be illustrated using just few such descriptors like bond length. And this is one illustration. The other one is the sensitivity to the bond angle. And again, you can vary the bond angle between the central atom and its two nearest neighbors, and you get this huge response. And you can do what we did in our work. We were not the first, but we did it the first time for this purpose, when we showed that different atoms in a nanoparticle have unique response. Like a black one, which is embedded inside, almost like a bulb, has the XANES signal corresponding mostly to what we expect to see in the bulk platinum. And the more under-coordinated it is, like red, yellow, or green, the more changes you start seeing in the calculated spectrum. So this is yet another sensitivity of XANES to the structure. And this is all examples of forward modeling, where you start with the structure, you get the spectrum. That's yet another example where, from our recent work, I don't know if you see the citation, because in my screen it's covered by this Zoom things, but you may be able to see it probably. If not, I can tell me and I can move that Zoom icons away. But anyway, so this shows that if we have bimetallics and on the left you have palladium edge, and on the right you have gold edge, you may model what experiment shows very strong sensitivity of XANES to the distribution of elements within the bimetallic nanoparticle. You see some isosbestic points, you see some maxima, minima, and shifts, and all this can be roughly matched with the theoretical predictions. So yes, theory, so there are two take-home sort of lessons out of it, is that XANES is sensitive to important variations in local geometry, important for functional applications. For example, in catalysis, we care about distances, we care about coordination numbers. And the other thing that we know is that there is a need to extract it from the data, but we only can do it in one direction, from structure to spectrum. So that is probably after this slide, I'll make a brief stop. I don't think I spent, about 10 minutes through my talk. So the current state of the art can be summarized as what we can do with XANES is we can we have a lot of flexibility with the current codes by starting with a given structure and obtain the calculation of XANES that we can compare with experiment. And that's why this arrow here is that we wanted to really compare the calculation with experiment, but we cannot do quantitative fitting. Yes, there are some codes which allow in some limited circumstances to do that, but I'm focusing primarily on the limitations, not on the state where you can do it in certain cases. So the limitation is that you can start with a code, use various type of approximations, start with the structure, use various approximations, obtain the theoretical XANES. But what we do need is we need to solve inverse problem. So we need to map the spectrum to the structure. So we need to start with the spectrum and obtain the structure. And there are no equations for that, and it should be model independent. So that's where we applied our machine learning approach to invert this relationship by taking advantage of the state of the art with these theoretical codes that provide plenty of opportunities to do training of the neural net. So I'll make a brief stop after this slide, because I wanted to show you the main idea. So the main idea is this: we treat the problem as any problem of regression, where you have an unknown relationship between the input and output, an unknown function, and you want to find that function and invert it. So that what is, in our case, input is the spectrum, and what is the output is the set of descriptors, numbers, that in the output layer will be given by this function that tells us, for example, what coordination numbers of nearest neighbors correspond to the spectrum that is discretized in the input layer. And as any function can be approximated by this neural network, so should this function be, because it's a well-behaved function, as we demonstrated in the previous examples. And for that, we constructed this philosophy that is not different from any philosophy of using an artificial neural network, also known as multi-layer perceptron, as I learned today. The input is from the experiment. Neural network is doing this number crunching, getting the descriptors. From the descriptors, such as coordination numbers, we do conventional modeling, like we do with XAFS coordination numbers, and predict the structure. And in order to make it work, neural network should have all these weights and biases found, and for that we need to do training. So this is our objective, to do that, and in the remainder part I'll show you how it's done and some examples, but I'll stop for questions. Should I stop sharing or?
No, keep sharing, keep sharing.
Okay, I'm sharing.
That's a great start, Anatoly, thank you. And yes, people can see the citations down at the bottom, there's not a problem. Okay. First question for you is, there are, of course, many spectroscopies other than XAFS, though perhaps it's blasphemy to admit it. How widely used are these kinds of machine learning methods across other spectroscopies, NMR, Raman, and so on?
So I will discuss it in the end, but soon after our first paper appeared, we had very nice paper. We learned about very nice work done using EELS, electron energy loss spectroscopy, which is of course very similar to XANES in terms of information it contains, where people also used some version of machine learning neural network to predict EELS spectra from the different structures. But it was not inverted in the way we did, but I think it has all the attributes that it would be successful if it's done right. So my quick answer to this question is that as long as there is, well, there are several sort of prerequisites for this method to work. It needs to be, there should be contrast to the descriptors. And so in order to make this method work, I demonstrated that XANES does have the contrast. There should be ability to do training. And if the neural network has, you know, many hyperparameters, a lot of nodes, you need to provide a lot of training sets, and it should be therefore theoretically generated, not experimentally. And they should be labeled. So if you don't have labeled data sets from experiment, you're stuck. You need to have a theory that could give you this training. And so I'm not so familiar with Raman, but we will try to find time to look into it to see how much we could do. But some people already are encouraging us that in some limited variations of structures, Raman spectra can be put in the one-to-one correspondence for the structures, and for that reason it could be inverted. I know it's a very long answer, but I have some more ideas. But let's move to the next question.
Okay, that's good. There's a number of questions. Matthew Marcus, do you want to ask your question while I catch up on the chat?
Yeah, actually, PFAL Solar Power asked how is the neural network trained before I got there. And I was saying, I'm assuming the training data is a set of forward modeled spectra. And my experience in XANES modeling or XAFS is that you have to make some realistic assumption about delta sigma square for each path. And so how do you do that? And likewise at 0 squared, because those make big differences.
Well, probably very problem specifics where you mean you're talking about the Debye-Waller factor, where disorder affects the data should be done on a case-by-case basis. In fact, our recent work, we're investigating some materials show the effect of disorder may be important, but on a first approximation, we can ignore it because the K values for XAFS oscillations are so small in the XANES region that sigma squared, you know, the Debye-Waller factor doesn't give significant contribution.
Right,
but
how about S0 square?
Sorry?
How about S0 square?
Oh, S0 square, right. So that's a very good point. So we impose S0 squared to what we find from XAFS analysis of some reference materials. So yeah, this is a very important point. Thank you for bringing it up. Yeah, I'll probably mention it.
All right, John Rare, you had a question?
It was a comment, Anatoly. I said that XAFS analysis is usually based on some subtraction of a background and then a fine structure. And it's the fine structure that has most of the structural signal. Is that at all useful in this machine learning, or does the machine learning automatically do background subtraction for you?
I see what you're saying. So when we apply machine learning to XAFS analysis, we do our own background subtraction. And then we take XAFS data, and then and I will show how to do it. But when we deal with XANES, we of course don't worry about background subtractions. So what I'm showing right now is just the application to the XANES. But for XAFS, I will mention in the rest of the talk how we deal with background subtraction, I hope.
But my question is why not do it in XANES too? The XANES actually has the density of states, times a smooth background.
Well, so a brief answer is we are not aiming at quantitative agreement between the XANES spectrum and the experimental data, because what we are doing is we are absolutely aware that maybe this background flexibility causes additional descriptor to the spectrum, but because this method works experimentally verified, its method works when you map the spectrum on even a sub. We don't have to know the full set of descriptors. One of them can be background parameters. If we successfully map it on the subset of the descriptors and the goal is achieved, that's for us for now is deliverable. But it would be important, and actually this is what my group is working on, to find out what is the total amount of information available in the XANES. And this is a very good point you brought up, that this flexibility to the data processing is yet another descriptor that is kind of like a parasitic one, but important to take into consideration. It does affect the data. So we have the sort of operational answer we can do without thinking about that too much, but also we're aware of the information limit on the spectrum.
Okay, thank you. Are you going to tell us more about detailed implementation next?
Yeah, actually, I'm only like 35% for the talk, so let me go through.
Okay, good. Yeah, there's some questions about details, but I'll give you a chance.
I probably will answer a lot of questions through the talk. So
yeah, we'll go back to those at your next break. Okay, very good. You should continue. Thank you.
Sure. Okay, so this is kind of a preview. So I thought if I will be completely out of time, then this will be a success if I'll get here. So now I can move on. Okay, so in the original paper, and I should give full credit to my former group member, postdoc Yanis who basically single-handedly developed this technical approach by using his ideas on how to construct training set and many other things that he contributed. But this is a pleasure to really follow that story as it was developing 3 or 4 years ago. First, what we did is we wanted to have a good controlled experiment to understand whether the results that we predict from the neural network can be trusted, because obviously for obvious reasons. So it's very difficult to find such labeled data sets for which you know the answer from XANES, because that's circular reasoning. So we fortunately had access to experimental data from our previous works. On the bottom left, there are citations where we had analyzed very well-defined platinum nanoparticles made by our collaborators, very monodispersed with a given size distribution, with different sizes. And you see that the XANES there showed very strong contrast from smallest to largest. And we thought, whatever we get from this neural network, we will be able to compare against the results that we knew independently from XAS analysis of those particles. And so the next step was to understand what are we comparing with this experiment. We cannot compare the XANES of individual atom in the particle, although it looks very, very different. But that's not the difference that you see in the experimental data, because in the experimental data, all the contributions are averaged over the ensemble, and these curves on the left show individual contributions. So we thought, well, let's see if we average them over this ensemble within a given type of polyhedral particle, will they survive? Will their contrast survive? And it did. And Dominique Bézin, a long time ago, did similar exercise, if maybe many of you remember, in 1997, I think, with earlier FEF versions, and he obtained similar results like here, that there is a big dependence on size of the XANES, and we confirmed that. So this already gives us some resemblance between the data and the particle average structures. So this was kind of a prerequisite for anyone who wants to try a neural network for new systems, to see if there is if the data support that approach. So question then, how can we extract this information about the particle size and shape and basically coordination numbers from the data? So for that, we use this supervised machine learning approach. So we need to construct training sets. So there are several requirements for this method to work. Is that it needs to be labeled, because in order to fix the values of those weights and biases in the nodes in the neural network architecture, we need to have the knowledge of the relationship between the spectrum and the descriptors. And only with that knowledge, the program can find the loss or the cost function that it wants to minimize, the difference between the initialized values of the output and the calculated values. And only by knowing that difference, it can find the minimum in the parameter space where the weights and biases have the right values. So this is the purpose of training. And so we need to have this data. And where do we get them from? Well, maybe in some cases we have good experimental data, but turns out that we need to have a lot of them, because we have a lot of these hyperparameters. The XANES spectrum, to discretize it, you need to have at least a few tenths, maybe hundreds of energy points, because XANES changes quite fast. And the absorption coefficient, I mean. And for that, you need to have at least a lot of, maybe tens to hundreds of input nodes. And then you have some deep layers, maybe 2 or 3. And each of them may have like 15 to 30 different nodes based on your situation. That's what we use. And so you can easily get hundreds of thousands of training sets that you must have to nail down those weights and biases so that the neural network will be ready to analyze the unknown spectrum. And therefore, you cannot train on the experimental data. You don't have so many labeled data sets. So that's the constraint. And we needed to decide how to use theory for that. And we needed to decide how to validate the neural network. And of course, there is a standard procedure. You withdraw 20% of your data from training. But we also wanted to use experimental data to validate, because nobody will believe that it will be useful. So we need to have experimental data for which we know the ground truth. So I'll just walk you through the footsteps that we did, just because some of it was dead end, but I think it's very good learning experience. What we tried to do was the most logical thing. Let's generate as many different polyhedral structures as possible, sources of this training set, calculate XANES on all of them, and see what type of training we can get. And we have no shortage of imagination to generate various type of polyhedra, like shown here. And we used them, and some of them in our previous work for XAS analysis, so it was easiest start. But then we understood something which was very unfortunate, that for those structures, the larger they are, the more similar XANES becomes, because it will be dominated by the bulk atoms. And they are not therefore good for training purposes, because there is degeneracy, so you're really not adding any more training sets if you add large particles like this. But for small particles, you quickly run out of options, what unique structures you can generate. So XANES came up with a new approach where he simply mixed and matched combinatorially atoms from different particles shown here. They were like, 60 or so generator particles. And he took, for example, this atom from this particle, this atom from this particle, this atom from this particle, combined them and obtained this artificial XANES. And because of this combinatorial relationship, there was very large number of such combinations, easily reaching hundreds of thousands of spectra, and they provided sufficient contrast between them to be used for this purpose. So the validation was done using particle average structure. None of them was used in the training set, obviously. And you see that for them, we knew the ground truth, because we could calculate for all of them what the coordination numbers are. And there was very nice behavior that all neural network papers show as success, where you show the agreement between the predicted value and the ground truth for the first neighbor, second neighbor, third neighbor, fourth neighbor coordination number. And if you remember, it's exactly what we need to know from XAFS to reconstruct the particle shape by this method for polyhedra. Except that here we didn't have to use XAFS, but our results would be as good. But the proof would be not theoretical, but experimental. If we really can get for the same structures for which we get XAFS data, if we can get for the same structures from XANES data, the same results as for XAFS. So this is done here. We had this, as I told you earlier, we have this 10 or so spectra with well-defined particle shapes. We did XAFS analysis in 2009, 2010, and we got the coordination numbers that we could trust. But interestingly, we could only trust the first, probably the second, but the third and the fourth were already very difficult to get reliably because of the interference with multiple scattering contributions were important, and for nanoparticles, they were not always easy to reliably measure or account for. So we found that this neural network actually is better than XAFS method, because there is no problem with the multiple scatterings. You just map it on the pair coordination, and that's it. And it's similar how PRDF method works in diffraction, that you just get pair information. So first thing is that the first nearest neighbor coordination number was in very good agreement between our method, which is vertical axis, and the XAFS method, which is horizontal axis. They're all on diagonal. For the second nearest neighbor, third and fourth, I told you that we already could not use XAFS as the ground truth. They were so difficult to extract for those particles. And instead, what we did is we used correlation between the first and the second, first and the third, first and the fourth. And it turns out that there cannot be two wildly related to each other. There is like an island where most of these theoretical particles are located. A lot of them, we calculated, have predicted values to be within this island, and our values obtained from our analysis are smack within this predicted island, this expected sort of island of existence for second, third, and fourth. And so for us, this was a sanity check or reality check that this is reliable, because there was no ground truth from XAS. And this is the, so after this, I will make one more stop, because I want to show to you the forward-looking sort of slide that shows that what we were able to accomplish with XANES is to get coordination numbers and distances, which I didn't tell you much, but it's the same idea. And from that, we could obtain characteristics of monometallic particles, bimetallic particles, clusters, non-metallic objects, and follow this in operando condition. It's all described in the papers that are in the end of this presentation. And but the principle is the same. You start with either one neural network for monometallic, or with two neural networks, one for one element edge, the other for the other element edge, and obtain information for partial coordination numbers. And what we thought, again, sort of like in a casual conversation, Yannis and I thought, why can't we do it for XAS? And we started to think, like, what new information can it give us other than the existing one? And we thought that it would be really cool if we could map the data not on the coordination numbers, but on the whole PDF or G of R. And it would be useful not just because we could, but in some cases, as we all know, the way how coordination numbers are determined, or any XAS data, depends very much on the assumption that the distribution of neighbors is quasi-symmetric or almost symmetric. Because if you have strong disorder, not symmetric disorder, then the higher order cumulants in the cumulant expansion will be important, and those cannot be found from the fit. Too much information in the theory to extract. And for that reason, the XAS analysis has this bottleneck, very well known, that you can't use it for very disordered materials. But the information is in the spectrum, except that if we write the original XAS equation, it will have G of R under the integral. So in principle, if you knew the G of R, you could obtain the XAS spectrum theoretically. And then it's the same philosophy. If you knew that, you can obtain it, and then you can invert it to map it back on the G of R that is in the unknown material. So the idea is that we discretize our G of R, let's say 30 different bins in the histogram. And if we consider the occupancy of each bin as the unknown or the descriptor, then instead of, let's say, 2 descriptors or 4 descriptors like coordination numbers, we'll have 30 descriptors. But the same idea. Input is the data, output is the value of the G of R, and we can get it not only for a given material, but follow the transformation from ordered state of one type to ordered state like FCC, in this case of iron transition from BCC to FCC at high temperature, where we not only follow the transition before measuring the data before and after, but we managed to obtain the change in the G of R during this very disordered state when it transformed from one to the other, which is not possible by conventional XAS, because you can't use any of the XAS equations to describe that. Molecular dynamics probably is an alternative, but that's a different story whatsoever. So in order to make it work, we needed to take some careful look at the input. How do we take full advantage of the data? So we took advantage of wavelet transform as an input, not the case space. And I will show a few things in the next slide. But let's make a quick stop to capture the main ideas here and answer questions. How I'm doing with time, Jerry, in general? You wanted to finish
all good. All good. Don't worry about it. Time is fine. First, William, you had a few questions, I think.
Yeah, let me unmute myself. Thanks for the interesting talk. So one question is that it's often customary, right, with these neural net trainings on data sets where you can just do the forward direction, is to sort of decapitate the end of the network and then train on some experimental data sets. Have you done that to do this sort of transfer learning to real data so that you get used to things like any experimental artifacts that aren't in the simulated patterns?
Very interesting that you brought it up, because we have weekly group meetings, and just today we talked about this in a different concept, but we did not do it for this multi-layer perceptron or artificial neural network, because we didn't want to bias neural network to be informed by experimental data, but that can be debated. We do it for another approach that we're developing currently. But yes, we do it as a style transfer, transfer learning, like you said, but not for the artificial neural network. It might be useful. I'm not prepared to really discuss it in detail. I'm also learning, dynamically how this transfer learning can work. But
and then the other question is like, so in this case, you're doing something similar to what we've done with small angle neutron scattering data, where you calculate a gazillion patterns of simulated data to train your network on. So in some sense, I was originally asking, like, you've made your data set available, but okay, anybody can generate this, but is your code available, I guess, on GitHub or somewhere publicly for people to play with?
yes, so I can, if you email me, I'll put you in touch with our students, and in papers we give this information either in the appendix. What we did in the latest paper, we tried to even include the notebook. Well, basically we use Mathematica, we use various type of public software like TensorFlow using Python, but lately we've used Mathematica notebooks that we can share, and it's very short sequence of commands how to train neural network, because it's all built in the Mathematica, so we can share that and let people use it. Yes.
Okay, so I don't want to monopolize the discussion. I mean, I have an additional question, but maybe you could come back to me if other people are done.
Okay, let's see if there are other questions at this stage. Jerry, you're muted.
I muted myself. Evan, do you have a question?
Hi, I have a question for you, Anatoly. I guess this is an implementation question. Since you are using theoretical spectra in order to try and train a neural network to, reach conclusions about experimental data, I was wondering if you could talk a little bit about the considerations that go into establishing the energy scale of the simulated spectra. Specifically, I'm wondering, in general, do you think you should be constraining yourself to, say, experimental SIP files instead of DFT constructed structures? How you worry about treating the core whole, or how you calibrate the alignment between the theory and experiment?
Thank you very much. Very good question. So we are, in general, not very traumatized if the agreement or disagreement between theory and experiment in some standard cases is not so good, because I think that's what makes this approach so interesting, is that it doesn't rely on quantitative fit quality or some kind of cost function as a figure of merit. I mean, obviously some kind of cost function is included in the optimization process within neural network, but we don't rely on the minimization of the residual between the theory and the data. So to some degree, we can tolerate a mismatch, whether it's due to the including or not including core whole, or some other difference in theory and experiment, that would still make this method work, because the neural network does not rely on this quantitative agreement, but it has its own kind of good eye to detect features that are beyond human, to understand, like, derivatives, inflection points, and all these little things that happen when you break down the data into this, machinery of the neural network. What happens inside, it's also actually subject of major debates, how to visualize, what are those elementary features for recognition, right? But if we go too far with that, we will probably be wrong, because some kind of agreement should be expected. So we don't have that much statistics to tell one way or the other. From our limited experience summarized in the papers, we always start by trying to find the best set of either FEF or FDMNS parameters that would get best agreement between the theory and the data for some representative material, like a metal bulk, if we analyze metal particles, so metal oxide if we analyze nano oxides, and we go from there. And so far we didn't have exceptions, and we would be worried and start researching that if we did. So that's my evasive answer.
Okay, Yang Ha, you had a question?
Yeah, I just want to ask, so other than neural network, have you considered the other machine learning algorithms like random forest and?
Well, we read about that, but we didn't use it for our work because well, we will eventually venture to some kind of unsupervised learning to be able to do classification and other things when we have a mixture of different states. But for now, we're trying to use, and there's still plenty of applications where you have more or less homogeneous situation of a material that has a microscopic uniformity that each atom on average has similar environment. And for that, the question is, what is that environment? If you have a mixture, you need to recognize what species do you have, how many you have, and that's a different type of problems. So for these problems that I just tried to outline, we think that this supervised, artificial neural network regression method works. We didn't try the forest. We did try other methods, which is currently work in progress that I wanted to say will be summarized soon, somewhere, published elsewhere, hopefully. But yes, we're trying other methods too, but mostly this for now.
All right, thank you, Anatoly. You should continue.
Okay, let me see how much I left because probably we're close to the end anyway, and there are probably other questions as well. So I mentioned that to get the pay distribution function, you need to have neural network that can recognize the input as XAS spectrum, not XANES anymore. And it should be trained to find the relationship between the input and the pair distribution function that this sample contains. And we found that it's called feature engineering, that wavelet transform provides the good input for that. And we did this in this work shown here. And we demonstrated for the first time with the colleagues from Latvia, using their excellent data that they collected on very well-defined, very carefully designed experiment where iron was free of any carbon impurities, going all the way through 1100 Celsius, as I remember, forming FCC out of BCC. And so we followed this transformation and showed that this PRDF approach is really useful. And then we applied it to, and so it's shown here. So you have this data on the left at different temperatures, and you see for yourself how different structures are there at different temperatures, changing from this to this. And if you do Fourier transform, you will get this. But if you try to do conventional analysis, you will not be able to analyze the transition region. And for that, we had to do the radial distribution function extraction. And by using that, we were able to quantify what happens in the transition region or close to the transition region. And so this is how we demonstrated the usefulness of that. And after this was demonstrated for monometallic materials, we demonstrated it also for bimetallic. By some reason, I put this slide before that. I guess there was no reason to show this to you other than just to say what we accomplished so far in general. So the monometallic materials, including clusters, are on the left, the bimetallic are in the middle, and then the XAFS approach to the bimetallics is on the right. And it shows this Salvador Dali-like inset as the wavelet transform input for the data, and the Fourier transform is shown here for different conditions, different concentrations of the bimetallic compositions. And the data are shown here as a demonstration that molecular dynamic simulation and neural network can actually extract the same PDF information from the simulated data. And when we applied it to the experiment, I will show you in the end what was there. And here I'm simply showing to you some sort of capability that this combined methods provide. So suppose that you managed to map your spectrum into a set of descriptors. It could be coordination numbers, distances. I didn't talk about electronic descriptors. We're also thinking about using them as well, like some kind of energy shift to describe D-band center and catalysis. But suppose that you want to monitor these descriptors changing continuously as you move the material from one state to the other state, for example, in the course of chemical reaction, if it's a catalyst, or following the phase transformations, like in the case of iron. And as I said, it's very difficult to do conventionally because you have loss of sensitivity to the disorder in the middle of this transition. But in this case with iron, you can think of what we did by looking at this diagram where you train the neural network to recognize the relationships between these descriptors and the spectrum for some grid points, grid in this imaginary multidimensional space. And as you move the spectrum from one state to the other state, you are finding the nearest grid point or interpolate between the nearest grid points to obtain the actual structure or actual values of those descriptors at each point. And so this is the philosophy of neural network in general, supervised artificial neural network approach, where it's really nothing but interpolation, regression of the data. And so for that, you need forward modeling to construct those grid points. And these data points can be XAFs or XANES. The grid nodes can be theoretical XANES or XAFs, and the descriptors can be anything that you think the data depend on. And it's not that I tested all possible things, but it is probably logical to expect that what works for some descriptors should probably work for others. Okay, back to the example with the bimetallics. So why it was important to map XAFs to the pair distribution function and not to use conventional XAFs analysis. These are very difficult samples to analyze, partially because palladium in this sample, in the most important one, had only 2% atomic ratio to gold. And if you do conventional XAFs analysis with all the multiple scatterings, with all the complications, you probably would see very well the first nearest neighbor, but you will not see much beyond from the fitting. To take multiple scattering to this extreme takes a lot of care, low temperatures, very well-defined samples, and it's really very aggressive to apply it to get this information from multiple scattering analysis. But here we don't have multiple scattering, we have pairs. So here we could compare, for this particular sample, the PDF extracted from our method, which is solid line, and the PDF calculated for idealized structure relaxed using some reverse Monte Carlo simulation and molecular dynamics simulation. And you see that for the first nearest neighbor, you get good agreement, but for the higher order neighbors, you see a strong shift to the lower distances of the palladium gold bonds compared to the predicted from average structure, which is what reverse Monte Carlo simulation did. And the average structure was periodic, as given by Weber's law. And the actual structure seems to show shortening. And so we reasoned that this shortening of the distances can come from the surface location of palladium, because everybody knows that due to surface tension, the atoms in the surface are closer to each other than in the core. And so this is the advantage, a unique advantage of using a neural network approach for extracting PDF than trying to do other kind of XAFs analysis than that. And I will conclude very soon, but I just want to show some possible outlook for this. And the neural network calculations are very fast. So in principle, if you get data produced with quick XAFs fast during the measurements, you can actually analyze it on the fly. Or by saying you, I mean the neural network, if you have the data acquisition computer outfitted with this neural network program, which is actually very easy to do, then you can feed in the data, like kind of data pipeline that would spit out, you know, your coordination number. And suppose that your catalyst sinters and you want to know that. And you can see from the results that you see increased coordination numbers, or we can even map it on something more intelligent like coordination numbers, maybe some, you know, structural geometric attributes. That would immediately be obvious that you need to change something with your reaction conditions to compensate for that. If that causes catalyst deactivation, for example, you will know why. So this is useful to know on the fly, as opposed to sitting at home and analyzing the data like 1 month later. Obvious application to that is high energy resolution experiments. Matt mentioned HRFD earlier today. Hopefully HRFD is one example where it can be used by this method, because the only thing you need is the contrast. The better contrast, the more sensitivity to these features you have. And we see here how HRFD improves the sensitivity of XANES to the structure and absorption properties of some platinum catalyst that we investigated earlier. And I should mention, of course, Jerry's own work, where hopefully benchtops XAS thing that requires just XANES, that can reach XANES with good quality. But for this method, we don't need anything else. So we can use this neural network to help Jerry. He probably already uses that in some way, but if he needs help, this can be incorporated in his philosophy to use lab-based XAS apparatus. And this can be done for analyzing the data in some cases. And some futuristic thing that we put in the perspective in the SES catalysis, that the bottleneck in the catalysis design is really to know what did you synthesize. We all know what we want to synthesize to make a catalyst active, but how do we know what was actually synthesized? And so our approach allows to link the spectrum to the structure and answer this question, and then get the optimization. And as I already mentioned, there are some reviews and a bunch of papers on each aspect of this, including different type of applications. And you can contact my group. And I want to give huge credit to XANES, who left us 2 years ago for Fritz Haber. And my current group running machine learning methods include Nick Marcel and Yang Liu, graduate students, and Prahlad Rus, a postdoc. And I think that concludes my talk. So now I will be ready for more questions.
It was excellent, Anatoly. Thank you. I'll start with a question. So extended EXAFS and high energy X-ray diffraction, XRD, have different strengths and weaknesses. There are a few papers that are starting to come out that try to synthesize the two. Do you think that could be an interesting future direction with machine learning?
Yes, that's actually interesting. How many people think alike? But one of our groups, one of the teams in my group, deal exactly with that. We're trying to reconcile the PDF from high energy diffraction, electron diffraction, neutron diffraction, and PDF extracted from XAS. And we're still in the process of scratching our head, asking ourselves, okay, so we will reconcile them, now what? So, but it is a very attractive new step, yes.
Very good. Matt Newville, you had a question?
Yeah, thanks, Anatoly. I may have missed it, but I didn't actually see any error description or values reported in anything you. So in these publications, how are you reporting uncertainties, and how do you just derive those uncertainties from this analysis?
So all publications, including this one that you see, have uncertainties. The vertical error bars are uncertainties from the neural network calculation. The horizontal.
What effects go into those uncertainties?
So there are many considerations. In the initial paper, we treated uncertainties very similar how we treated them in the early stages of XAS analysis, where we simply found the difference in the results for different scans. And you remember there was a period of time where we reported this as an error bar. But then here we also changed the hyperparameters in the neural network, and they produced slightly different results, and we considered this as a measure of the uncertainty. In the latest papers, we included more statistically meaningful methods, like I think it was either validation loss or some kind of loss. I think I'm correct, remembering at least one word out of two. But it's all this. So the latest paper shown. Let me show you the reference.
So I'm a little confused. I'm a little confused because you said that it wasn't sensitive to a cost function. So how do you evaluate the change?
It was not sensitive to what function?
A cost function. You said that the neural network was not optimizing against a cost function.
Oh, the cost function. No, I did not mean that. I meant that it was not optimizing for, hold on, let me think. I misspoke there, Matt, I apologize. Yes, there was optimization of the cost function. What I really meant to say is that that XAS analysis, as we know it, relies not only on the produced results, but also on the visual examination of the fit quality, because we know where we expect to have a fit and what does it mean that we have a theory producing peak in a certain region. But there is no such expectation in the neural network. And I did not mean to say there is no cost function. There is. And so the errors in the latest reincarnation of our method are obtained using the cost function, but not similar to XAS, like, you know, using the Hessian matrix or something like that. There's a different approach for that, but there is one.
Matthew Marcus, you had a question?
Yes, I had several effects that don't seem to be taken into account. Like, for instance, interactions with the substrate or electronic effects would do things like change the white line intensity. And on your copper 4 cluster, like in this slide, every copper atom is connected to a substrate oxygen atom. So that's got to do something to it. And so I'm wondering how that is taken into account. And also,
go ahead.
And also in the G of R, of course, what XAS depends a lot on the multiple scattering. So that depends not just on G of R, but on higher order functions. I guess what you're getting is an effective G of R.
Right. So both of your questions are related to one approach that we used. Strangely, it answers both questions. For the first question, yes, not only that there are oxygen atoms from the support that affect different copper ions differently, but each copper, in some of our work, not in the one shown here, where we used copper clusters which are oxidized, each copper is surrounded by oxygens as well through the oxide. So we found experimentally that it is not necessary to find all possible descriptors, which would be impossible because of the very large number of parameters. But if you can map the spectrum on the subset of those descriptors, so for the copper clusters, we focused not on copper-oxygen interaction, which would be very subjective, because each cluster may have different, or there may be a lot of heterogeneity, but we focused on copper-copper interaction. So we were able to map the spectrum of these small clusters on copper-copper coordination numbers, which were not the first nearest neighbor, but second nearest neighbor, similar to what we did for monometallic nanoparticle. So we completely ignored oxygen bonds. For the second question, it's the similar idea. We know that XAF spectrum is informed by multiple scatterings, but we elected not to map on everything we could, but map only on the subset of the parameters, which include pair parameters, and it worked. So this does not mean that there is no correlation, but the neural network trained on hundreds of thousands of examples was able to deal with that.
I see. So it outputs the real G of R because that's what's in the input data in the training data set.
Yes.
And so it essentially learns to ignore or correct for the multiple scattering.
Exactly.
Cool. This is great stuff.